So, we've been talking about probability distributions in general. There are certain special kinds of probability distributions that apply in certain situations that come up often enough that it's worth knowing about them. And the one we're going to talk about today is what's called the binomial distribution. So before I tell you what's special about it that makes it the binomial distribution, let's look at some examples. Suppose 3 coins are flipped. It could be any number of coins, but in this example I'm pretending we're flipping 3 coins. Then the number of heads that come up could be 0, 1, 2, or 3. So if you do that, you toss 3 coins and you count how many of them come up heads. That number of heads that come up would be an example of a random variable. And we can list all the possibilities for that random variable. It could be 0, could be 1, could be 2, could be 3. And we could work out the probability of each one by counting all the different ways that the 3 coins could turn up, counting outcomes, how many of them give you 0 heads, 1 head, 2 heads, 3 heads. So there's the probabilities there, and so that gives us a probability distribution. Another example, if you invite 2 friends over for dinner, how many of them like broccoli? Could be 0, could be 1, could be 2. So that would be an example of a random variable. How many of the 2 friends you invite over like broccoli? And if each one has a 60% chance of liking broccoli, then the probability distribution for the random variable would look like this. X, that is the number of friends who like broccoli out of the 2 you invite over, could be 0, could be 1, or it could be 2. And then here are the probabilities for each of those. For now, don't worry too much about how I came up with these numbers. If you want me to explain it, I can say, well, the probability that you have 2 friends who both like broccoli would be, that means that the first one does and the second one does. So that would be 0.60 times 0.60. The probability that it's 0 would be the probability that the first one does not and the second one does not. So that would be 0.40 times 0.40. And then because all the probabilities have to add up to 1, the only thing the one in the middle could be is 0.48. That's the number that has to go there to make all 3 of them add up to 1. But for now, I'm not really focusing on how we get these probabilities. We'll say more about that today. Now, if you invited 4 friends over, then the number of those friends who like broccoli could be 0, could be 1, could be 2, could be 3, or could be 4. So then your probability distribution would look like this. The possible values for that random variable would be 0, 1, 2, 3, or 4. And the probability for each one, well, I've got them listed here. And right now, I really don't expect you to know how I came up with those probabilities. But today, one of the things we're going to talk about is there is a formula that gives you those probabilities in this kind of a situation. And if you don't want to bother using the formula, there's also a calculator function that you can use. And there's also a table in the back of the book that you can look those up on. Another example, a baseball player has 3 at-bats in a game. How many times does he get a hit? Well, it could be 0, could be 1, could be 2, or it could be all 3. Now suppose each time he comes up, he has a 0.3 probability of getting a hit. I might want to know, well, what's the probability that the number of hits he gets turns out to be 2? Remember, I said it could be 0, could be 1, could be 2, could be 3. If it could be 2, what's the probability of that? Well, the answer turns out to be Getting 2 hits would be like if he got a hit the first time up and a hit the second time up, and then he got a miss. He didn't get a hit the third time up. And the probability of that would be 0.3 times 0.3 times 0.7. Getting a hit the first time and getting a hit the second time and not getting a hit the third time. And that would come out to be 0.063. But that's not really the answer to the question of what's the probability that he gets 2 hits, because this is only one of the possible ways of getting 2 out of 3 hits. There are other ways. He could get a hit and then a miss and then a hit his third time up. Or he could miss the first time up and then hit the second and third times. So we'd have to multiply this by 3 to get the correct probability of 0.189. Now, you don't have to understand my reasoning here. I'm showing you this example because it's the reasoning behind the formula that I'm going to show you in just a minute here. So if you like knowing why formulas work, this is kind of an explanation of why that formula is going to work. But you don't have to know why it works to use it. What these examples have in common is each time an experiment is tried, there's one of 2 outcomes, which we could call success or failure. Either something happens or it doesn't happen. Either the coin comes up heads each time we flip, or it doesn't. It comes up tails. Either for each friend that you like, that you invite over, either that friend likes broccoli or they don't. Each time the batter is up to bat, either the batter gets a hit or he doesn't. So the word binomial, bi means 2. So binomial refers to the fact that there are 2 possibilities, or we can reduce it down to 2. So each trial, each time you try something, try to get a hit, try to flip a coin, try to invite somebody over for dinner, either something happens or it doesn't happen. So if you have a certain specific number of trials, a specific number of coin flips or friends invited over or at-bats, and the outcomes are independent of one another, so whether or not the baseball player gets a hit the first time up is not going to affect his chances of getting a hit the next time. Whether the first coin comes up heads is not going to affect the probability of the second coin coming up heads. And it's the same probability each time. So under this kind of a situation, a binomial distribution represents, it's a probability distribution where your random variable is the possible number of outcomes of that binomial experiment. That is, it's the number of successes, which could be anywhere from 0 to how many times you try it. The number of heads that come up could be anywhere from 0 to the number of coin tosses. The number of friends who like broccoli could be anywhere from 0 to how many you invite over. The number of hits the baseball player gets could be anywhere from 0 up to the number of times he's up to bat. So we have that list of possible numbers of successes together with the corresponding probabilities that there will be exactly this number of successes. So let me explain the notation. We're going to be using letters to stand for various things in these kinds of situations. So here's the notation we use. We use N to stand for the number of trials. So that would be like how many coins you toss, how many friends you invite over, how many times the baseball player is up to bat, that sort of thing. P, a lowercase p, represents the probability of success on each individual trial. So each coin has a 50% chance of coming up heads. Each friend has a 60% chance of liking broccoli. each time the baseball player's up to bat, he's got a 0.3 chance of getting a hit. So that's the P. Then Q represents the probability of failure on any individual trial. The probability that what we're talking about does not happen. And remember, the probability of something not happening is equal to 1 minus the probability of it happening. So Q is always going to be 1 minus whatever number P is. And then X will represent the number of successes. And remember, that could be anywhere from 0 up to N. So the kind of question we're going to be answering here is, given N and P, given a specific number of trials and a specific probability of success on any individual trial, we want to be able to find the probability of any particular number X of successes from 0 to N. How do we do that? Well, we got our choice. There's several different ways we could use. One way is to use the binomial probability formula. So there is a formula that we can plug these numbers into and do the calculations, and it'll spit out what the probability is. Another thing we could do is to use a binomial probability function on something like a graphing calculator. Or Excel has something like this built into it. Or there's websites that you can go to and type in the numbers for N and P and X, and it'll tell you the probability. So I'm going to show you how a few of those things work. And then another possibility, another way we could do this would be, there's a table in the back of your book, table B, that you can look up the probability. You go to the part of the table for the numbers you're using for N and P and X, and it will give you the probability. The formula looks like this. In a binomial experiment, the probability of exactly X number of successes out of N trials is, now these exclamation points are factorial symbols. And I haven't talked to you about those, but maybe you've learned about them somewhere else, maybe you haven't. If you haven't learned about them before, the best way to think about this is this part of the formula right here represents the number of ways you could get, this should say X out of N, X out of N successes. And on many calculators, there's a special button or a special function that you can use to calculate this part of the formula. It's usually labeled NCR. So instead of writing it like this with the exclamation points, I could say this is, you take the number for N, and then you push that NCR button, and then you put in the number for X. So that's the first part of the formula, and then you multiply that by P to the X power, and then you multiply that by Q to the N minus X power. So for example, if you want the probability of getting 11 successes out of 13 trials, if P equals 0.8. So N, the number of trials, would be 13 in this example. P is 0.8, X is 11. So if we use this formula, we're putting 13 for N here and also here. We're putting in 11 for X here and here and here. We're putting in 0.8 for P, and then the Q would be 1 minus P, so 1 minus 0.8 would be 0.2. So it looks like this. Now, to actually put something like this into a calculator, it's going to depend on what kind of calculator you have. Here's how it works on one common kind of calculator. I'm going to punch in 13 and hit the probability button and select NCR and then put in 11. So there's my 13 NCR 11 times 0.25 to the 11 power. Sorry, that should have been 0.8 to the 11 power times 0.2 to the 2 power. And it comes up as about 0.268.